In this video, we'll state some examples of vector spaces. We will not prove here that these are vector spaces, although we'll prove that some of them are later. Example. Column vectors are basically just finite lists of numbers. The infinite version of this, the set of infinite sequences, is a vector space. We define addition component-wise. If we have one sequence plus another sequence, we add the first components, add the second components, and so on. We also define scalar multiplication component-wise, just as with finite vectors. We multiply each element of the sequence by the scalar. And although we do not prove it, this addition and this scalar multiplication satisfy the requirements for a vector space. Example. The set of polynomials with the degree less than or equal to n, written P sub n, is a vector space. If you define the zero polynomial as not having a degree, as some people do, it must be thrown in by special fiat. We define addition and scalar multiplication in the natural way. That we learned in algebra, if we're adding two polynomials, we combine like terms, and if we're multiplying a polynomial by a scalar, we distribute this multiplication as we have been taught to do. Example. For a fixed n and m, the set of all n by m matrices is a vector space. Addition and scalar multiplication are defined as we have defined them in this course. It might seem like it would be confusing to sometimes call matrices vectors when we also sometimes multiply matrices by column vectors. But vector spaces don't interact. If we're working in the vector space of matrices, we won't be called upon to multiply a matrix by a column vector. That's not one of the two operations defined on a vector space. Example. The set of all functions defined on an interval is a vector space. If f and g are functions, f plus g is defined in the natural way. F plus g of x equals f of x plus g of x for every input x. Similarly, we define CF in the natural way. CF of x is C f of x for all inputs x. As an example of something that isn't a vector space, what if instead of looking at the set of polynomials of degree less than or equal to n, we looked at the set of polynomials of degree exactly n. For example, the set of all polynomials of degree exactly 2. This is not a vector space for a few reasons. The 0 polynomial isn't in there, but we could throw it in, just like we did with P sub n. A more serious problem is that it isn't closed under addition. X squared plus x plus 1 and negative x squared plus x plus 1 are both in the set of polynomials of degree exactly 2, but their sum is not. In this video, we've stated a few examples of vector spaces. In the next video, we'll prove that our last example, the set of functions, really is a vector space.